Hello. The first application of the hypothesis testing framework is to an over-identification test. So there are many different names of over-identification test, but I don't know. So the idea is there are more than enough instruments. So you have extra instruments. Then you can test. You can use the extra instruments to check another instrument's validity. So let's see what happens. So the model we consider is, as usual, like a linear regression model with exogenous variables and endogenous variables. And x2 is endogenous. And also, as usual, I define z as a vector of x1, all the exogenous variables included in the regression model, and excluded instruments, z2. So z2 is the excluded instruments. That's actually what you count. And remember, this dimension is m, and we assume that x dimension is k. So we would like to see if the instruments are all valid or not, if they are exogenous or not. And here a few more comments. Like earlier in maybe at the beginning of this chapter, I explained specification test in this way. So specification test, even if you reject the specification test, you don't know which assumption is wrong. So it tests if any of the assumptions is wrong or not. In this case, your null hypothesis is that all the assumptions are true, but the alternative is some of them is wrong, but it does not tell you which is wrong. So it is a specification test. In other words, even if you reject the null hypothesis, it does not tell you which instrument is valid and which is not. So, but still, it is useful to see if your instruments are valid. And also, second comment, obviously you have to have an over identification. So your instruments, the number of instruments must be greater than the number of endogenous variables. Otherwise, you cannot identify the epsilon. So epsilon is basically dependent on beta. So you cannot identify beta without satisfying the null hypothesis. If there is no over identification, if the beta is exactly identified, then we cannot test this hypothesis. Like, in other words, if you have two endogenous variables, you have two instruments, then you have no choice but to use them. Like, even if they are wrong, you don't know. Like, you don't know what happened. But if you have three, then you have one extra power information to test if all of them are fine or some are wrong. So this is the basic null hypothesis. And there you can think about, earlier I explained 4 different approaches. So you may think about at least 4 different ways to test the null hypothesis. I don't know, like some may not work, some may work, some may not. But I will introduce you the most famous approach to this example, to this null hypothesis. That is the criterion-based test, which is often named as the Sargon test. Sargon is the name of the statistician, maybe econometrician, who proposed this test for the first time, maybe. And so in some textbooks, they're Sargon, I forgot the name. So some textbooks give credits to different multiple scholars, but I forgot the names. Anyhow, Sargon is always included, and there may be more than Sargon who proposed a similar and the same idea as this. Anyhow, Sargon test. By the way, and also the different textbooks use different statistics and different definitions, different names, and but I try to unify as much as I can. So as you may know, there is no clear reference, there is no perfect reference similar to my lecture note, because I combine different theories and different notations, different results, and I try to make a unified framework that is that you can understand the best. So now this explanation is most similar to Newey and McFadden and Hansen's over-identification test. But it is an older version, so it may be updated. But surely there must be over-identification test. And I'm telling you because these tests, even though you may not remember what is the criterion-based test, that does not matter. But you are going to use Sargon test maybe at some point, or someone may ask you, why don't you do Sargon test in your paper, for example? Then you need to know this test. So this test or over-identification test is more popular and important and widely used than this name. So this name is not important. So it's my name. So what I call this type of test, but Sargon test in a specific case is more popular. Anyhow, Sargon test is based on the criterion function, and we will consider GMM criterion function because the IV regression model can be estimated by a GMM method, and GMM has it minimizes a criterion function which is defined in this way. Oh, whoops, cancel. So okay, this is the criterion function, and the moment condition. So the moment condition we utilize is the null hypothesis. I will explain why we are using the null hypothesis. The null hypothesis is what we are using. It is, so in that sense, it is a restricted model because we are relying on the null hypothesis. It is a restricted model, and then at exactly same as before, optimal weighting matrix and the moment functions, and beta hat minimizes the distance. This is the distance, and then the ideal is what you can show that if the null hypothesis is all true, in the end the Q criterion function must be true, because if this is true, then this must be true. Excuse me. So if the moment is 0, then the estimated moment function must be 0, close to 0. It must be close to 0, close to 0, close to 0. So then as a result, criterion function must be close to 0. That is the idea. So exactly this is what I said here. And if not, if the null hypothesis was wrong, then they cannot be the moment, it cannot be 0 at the same time. All the moments cannot be 0 at the same time, and some moments will be different from 0, or to make a wrong moment close to 0. So say all the other moments are 0, but there is a moment who is non-zero. Then because of this, you have to change the estimate to make them as close to 0 as possible. So lower this part and increase these moments. So in the end, all the moments will move away, will be different from 0, and that's the clue if the null hypothesis was wrong. And then simple, and then this is a criterion-based test remember, in the criterion-based test, standardization is not standard. And in this case, it's pretty simple. So this is why this test is famous. The standardization is simply multiplying n. That's it. And then it converges to chi-square distribution with the degrees of freedom equal to the number of over-identified dimensions, the number of extra instruments. So if you have 2 endogenous variables and 3 instruments, then the degrees of freedom will be 1. But if you have 2 endogenous variables but 5 instruments, then the degrees of freedom will be 3. So the number of extra is the degree of freedom, the parameter for the chi-square distribution. Also, this test, I call this Sargon test, but another famous name is J-test. So, I don't know why, but Sargon, maybe in his paper, he defined this test statistic as J. And so that's why, I think that's why it is called J-test. But I'm not so sure. But many people call this simply J-test, like we say T-test, F-test. So another alphabet is taken for another test statistic. So J-test is another common term for this test. Okay, so and as I said, we do not have any unrestricted estimator. So this is a restricted estimator, but our idea is that the unrestricted estimator does not exist, but does not cause any trouble. So it's nice. It's pretty simple. Okay, and we are going to but again, even if it is rejected, so if the J statistic is large, different from 0, it is always positive, and it is different from 0, greater than a certain critical value, then you reject the null hypothesis. But even if you reject the null hypothesis, you don't know what is wrong. That is what we are going to consider in the following video. So see you later.